So our first objective was to state that thermal energy can be completely converted into mechanical work, but we need a cyclical process if we're going to keep doing that for a period of time. We want to explain what's meant by degraded energy. We want to construct and analyze these Sankey diagrams, these energy flow diagrams, and then we want to outline the principal mechanisms involved with producing electrical power. I am having a flashback to topic 4, where I must have given you something in the packet where there was a problem that had a piston. Some of you asked me at that time what a piston was. Well, here we have a piston again. So a piston is just a cylinder that has one of the ends that can move. All right. So this is a closed chamber, but this one edge can move back and forth. So we will typically have a gas like inside the cylinder that we heat up, and as we heat it up, the pressure will increase, and this movable wall will get pushed on. Right? So we can use thermal energy, right, delivered to the gas to cause mechanical work, to physically push something and cause it to have a displacement, right? And when that happens in our car engines like multiple times a second. But unless we have some way to reset the piston, back to where it was, we can't continue to do work. So we need some sort of cyclical process that's going to extract that mechanical work, but then allow the piston to move back and allow us to do it again. So here, right, we're kind of showing that cyclical process where here's our piston, right? These are just valves that will deliver like new gas or new gasoline that we will combust. So these are just valves that let the gas in and then let it out. But we've attached our piston to this flywheel, right? And it's pretty clever. So we've attached we've attached the back of the piston to this, right? And then that's attached to this flywheel that you can just move around in a circle. And the inertia of the flywheel will cause the piston to move back up when the gas is expelled and the pressure goes down again. And then the piston's just sitting there waiting again for that gas to do work on it. And then keep moving the flywheel. And the flywheel would be attached to the other parts of your car to help propel the vehicle. But we need some sort of cyclical process if we're going to get heat to repeatedly do work. All right, were there any follow-up questions about what you read with that we can get thermal energy to do mechanical work, but we need some sort of cyclical process? Patrick?
I was talking about like a diesel engine.
Okay.
And it said like, I got kind of confused because it was saying for like internal combustion engine,
okay,
it like vaporizes the gasoline.
Okay.
And the spark, it lights it.
Sure.
And then it was saying something like for a diesel engine, it just puts like
no spark.
The diesel in
right.
with no spark on the upstroke, and then
right.
I got confused.
Yeah.
So and then it said something about like its own heat causing it.
Yeah. So first of all, I mean, I'll address your question. So the question is like, how the heck does a diesel engine do it if there's no spark? If there's no spark that's providing the combustion? Topic 10, which is our second look at thermal physics, goes into all of that stuff in a fair level of detail. But the answer to your question is, we can inject the diesel fuel, and we end up getting a very high pressure. Right? So the diesel engine is designed to cause really high pressure where we're housing that fuel. And just that tremendous pressure increase will cause the liquid diesel fuel to vaporize, right? So it is combustion, so it is like liquid to gas, right? That's combustion is not our term for that. But that high pressure is doing the job of the spark plug. The high pressure is causing that stuff in there to get hot enough that it will spontaneously combust. So sorry, that's not a great explanation, but yeah, it's a pretty neat thing. And in part, diesel engines are more efficient than gasoline engines. So like I was talking to Mr. Rick at lunch today about this. He was telling me I should buy a Volkswagen diesel because you could get, what did he say? You could get like 200 miles on 1 gallon of not 1 gallon, 1 tank. I thought he said 1 gallon, which is why like I was confused by it. Volkswagen diesel engine.
I know
right?
which one.
So the diesel engines do have super good fuel efficiency. So Matt, I cut you off. What were you saying?
I know, like my friend has the VW like Beetles, and
Okay.
that's from like 6-7 years ago.
Okay.
He got like 60 miles to the gallon then, like
Right.
diesel.
So diesel engines are super efficient. So my wife has a Prius, which gets pretty decent gas mileage, but not as good as a diesel engine. And this is actually stuff we're going to talk more about in this topic. But I think in large part, Patrick, because we don't need that ignition, because we don't need that spark,
Right.
I think that's the biggest factor that allows the diesel engine to be more efficient, to go more miles on a gallon of fuel. Jake?
Is that why they charge more for diesel gas?
No, it's not,
the
and they should.
process.
I don't understand why they charge more for diesel gas, because the processing is
Isn't it more
cheaper
crude?
than it is for gasoline. It is not always the case that diesel gas costs more. I wish I knew. It hasn't always been. I remember like when I was probably a little bit younger than you guys, my dad bought like a new truck, and he bought a diesel truck. He didn't care about the fuel efficiency, he didn't care about like saving the environment, like nobody cared about climate change at that point. But his was cheap, and like he wanted to pay for the cheaper gas. Diesel was cheaper at that time. And of course, as soon as he bought it, like diesel became more expensive. But it's not always the case that diesel is
I
more
think
expensive.
there's like a truck that the military uses that gets like 4 miles to the gallon of diesel.
4 miles to the gallon, so that's
Really heavy.
that's not very
That's
efficient.
diesel too.
Yeah, I mean, I have a pretty inefficient car, and I probably get 22 miles per gallon. All right, so our next objective involved degraded energy, right? And this isn't really a new, it's not really a new concept for us. It's just a new name. So anytime that we're trying to convert one form of energy into another form of energy, we don't end up getting 100% efficiency. We don't end up converting 100% of our starting energy form to our desired energy form. All right. So we know energy has to be conserved, but we don't always get the transformation that we want. So some of our energy might end up going into a less usable form than we're trying to get it to go into. That energy is known as degraded energy. So an example that I'm illustrating here is like a mechanical watch. So a watch that actually has like hands that go around. Jordan, is your watch a mechanical watch?
Yeah.
Yeah, so Jordan's wearing a watch that actually has like a second hand and a minute hand and an hour hand. So his watch is, and does it have a battery? Do you have to wind it up, or what's the deal?
I had one that winds when you walk, but
Okay.
it broke. But this one's a battery.
All right, so Jordan's got a battery in there, and the battery is changing chemical energy into electrical energy, and then the electrical energy is getting converted into kinetic energy to move those hands. But it's not perfect, right? There's going to be some friction involved. Can you hear clicking or no?
No.
No. All right, so some watches you can hear clicking. I bet if we put our ear up against the clock up there, we could hear some clicking. So the clicking, the acoustic energy would be degraded energy. Any thermal energy that's produced would be a degraded energy, right? Just a less usable form of the energy. Why the heck am I talking about? I don't know why I'm talking about elastic potential energy for mechanical.
Is that what you're doing?
Well, okay, yeah, probably the kind you want. That makes sense, right? If we wind it, we are storing energy that way, and then yeah, it's converted to acoustic and thermal. Thanks. Okay, so again, this less usable form of energy is called degraded energy. I'd love to come up with another few examples of degraded energy. So maybe let me give you like a minute and a half in your foursomes. Think of some other process besides the watch. I suppose it could be one that you read about in the textbook that has an example of degraded energy in it.
Refrigerator. Never mind, I don't think that's pretty efficient to me.
So the spaceship takes off.
Yeah, there's a lot of gas goes in. I think it's true.
Good idea.
Well, I think
We like it.
the loud noise is breaking the sound barrier, but still makes a loud noise.
Alright, this group is on like their 8th example, so I think we're probably ready. Christina, what's the favorite one that you're going to talk about? Like what kind of engine? Okay, fine. So like my car engine is actually pretty loud. right? So that whatever acoustic energy it is producing is certainly not the most usable form of energy. It's not why I have the engine there. Yeah. My wife's Prius, not so loud, right? Not so loud. Sarah, what was your favorite that your group came up with? A light bulb? Yep. Right, so a light bulb, we're probably using it to make light, but we also can make heat. So that would be a degraded form of energy, sure. Amanda, what was the favorite one from your group? Laptop. 2 days ago, I took my laptop out of my bag when I got home, and like it was ridiculously hot. Like it should have been like in sleep mode or something, and I got really worried and I shut it down. But even if they're working normally, they produce heat as well, and that's not what we use them for. We use them for computing and for storing things, so for sure. Andrew, what was one that your group came up with?
Gunpowder.
Gunpowder. Okay, and what's the degraded form there?
Acoustic.
Acoustic, all right. So when we have the chemical reaction that hopefully takes stored energy in the gunpowder, changes it into kinetic energy of our projectile, yeah, it's pretty loud, and that acoustic probably isn't your most desirable form of energy. Well, unless it's like our starter's pistol or something, and then it is, right? Yeah, Jake.
You said light too, right? For that?
Yeah, sure. And Matt, what was your favorite one from your group?
Well, we said like jet engines, so.
Okay, yeah. So a jet engine, super loud. Yeah, super loud for sure. Yeah, Patrick.
Something like a toaster oven would be like really efficient.
Ha! You don't print out the notes, right?
No.
Alright, because I think toaster oven's the example we're going to do a Sankey diagram for later. So hold on to the toaster oven. Wow, that's eerie that we both thought of toaster oven. So we often keep track, in this topic, in IB physics, we keep track of our degraded energies by making these Sankey diagrams, these energy flow diagrams. Okay? So this example is for, I think the one that Sarah talked to us about, the light bulb. And the way that we construct these things, which hopefully you already read about, is for whatever reason, we always point them to the right. Okay, I don't know why. I guess because most of us are right-handed, and it's easier to draw things to the right than to the left. Sorry, lefties. So we draw them to the right, and we start with our input energy. So we start with our starting form of energy. So this is for a light bulb. So in this case, this would be our electrical energy that is getting put into the light bulb. And then the light bulb converts that electrical energy into other forms of energy. The degraded form, as Sarah already talked about, is thermal energy. So we veer the degraded energies off the Sankey diagram either towards the top or we could go towards the bottom. All right, so the degraded forms of energy, we veer off all of our energy is heading towards the right. We veer it off up or down. So this would be the thermal that the light bulb is producing. And then our desirable energy, our output energy, still points to the right when we get to the end of the diagram. So that's our light energy. So Patrick asked about efficiencies. The Sankey diagram tells us the efficiency. The efficiency is like the power out over power in, but it's only the useful power that we want to consider. So if we divide the amount of light energy by the amount of electrical energy, that would give us the efficiency, and multiply it by 100, that would give us the efficiency. And the width of these arrows is proportional to the amount of energy. So how efficient is this light bulb, roughly? Yeah, maybe 50, maybe even 40. It looks to me like the light one might be, this one's messed up, it gets thinner up here, it shouldn't do that. But if I look down here, maybe this is a little bit thinner than that. But they're roughly equal, right, so about 50%. So this would be an incandescent bulb, not like one of our fluorescent ones. Yeah, Isaac?
I don't know if this is in the reading and
Okay.
I missed it or something, but is there a difference with the direction that the arrows are going off in? Because it could go up or down?
Nope.
No? Okay.
Nope. No, well, not really. No, there's not. However, there is one feature that I'll point out in a bit that might tiny bit control that. So here is a more complicated Sankey diagram. There are a lot more degraded energies present here than in the light bulb one. This is probably for a power plant or some sort of generator. So we have an energy in, right? We are pointing to the right. The arrows aren't as pretty as the last one. We're losing energy in something called a condenser, right? So a condenser is probably taking a gaseous, a gas and changing it into a liquid. We are somehow losing energy due to friction. We're somehow losing energy with smoke, leaving the system. We're losing energy by an alternator, maybe bringing energy to other parts. And then we do have our output energy here. So this one's not really doing as good of a job at identifying the types of energy, but it is showing it's giving us some information about where the degradation is occurring. How efficient is this one? Yeah, let's make maybe more than 20, maybe 30. Yeah, 30, something like that. Something like that. All right, and again, this does label useful energy as yellow, and then all these other ones, this is called lost energy, but we're calling those degraded energies. So those are a couple of examples. So we are going to be doing Sankey diagrams for all of the types of power plants that we look at over the next few weeks. We already mentioned that we can calculate efficiency off of these things just by dividing the width of the arrow all the way on the right to the initial width on the left. And as I said before, we would calculate the efficiency by dividing the right width or the useful energy by the left width or the total energy. But then if we want percent, we have to multiply it by 100. The other thing that apparently I left out of the notes, if we have multiple degraded energies, we want to veer them off in the order that they become degraded. So, what do I mean by that? In this example of our alleged power plant, we have combustion of some sort of fuel, right? So smoke or whatever, we have hot gases that are escaping. That's probably going to happen as soon as the combustion occurs. So we are veering that arrow off first. The friction probably isn't occurring until later on where we have moving parts. So that's getting veered off later. So we do want to veer these off in the order that those energies are leaving the system. All right, Patrick?
Should we be consistent with which way the arrows branch off?
Well, I mean, if we have this many, there's 4 degraded energies here. I'm a little bit surprised. No, there's 5. I'm a little bit surprised that all of these 3 come down below. But no, I think it's smart to do both, top and bottom, so that it's just less. Things are a little more spread out, a little easier to see. I'd rather have some coming out the top and some coming out the bottom than just having the bottom, be super busy, right? Liam.
How does the pump work?
Say it again. The pump. Yeah, so apparently we're robbing some of the energy, maybe heat energy or maybe electrical energy at the end, to do something with maybe injecting fuel, running a conveyor belt that might deliver coal to our combustion chamber, or pressure. I don't know. We're getting some energy to go back into that initial part. Maybe for fuel delivery, maybe for something else. I don't know. So let's do one on our own. So I picked one that I thought was easy, but not as easy as a light bulb. So I'd like us to come up with a Sankey diagram for a toaster oven, which I suppose would be the same as a regular toaster. Toaster oven kind of has like the door, right? The toast doesn't just like pop right up. But I think the first thing you need to do is estimate the efficiency, right? So how much of the input energy, the electrical energy, really gets delivered to the bread itself and causes the toasting. So that should be your first step, and then you should try and identify different forms of degraded energy and then work on veering them off in a diagram. All right, so maybe we'll go 5 minutes on this and then get some representative sketch on the board.
Okay, let's see.